All right, here's 7.2. It'll be our only video here for sampling proportions is what we're getting into. Okay, so in the first section of Chapter 7, we talked a lot about just sampling distributions and some of their basic characteristics, and more than anything, kind of what they are and what they do. Okay, they tell us how repeated samples would vary. But here we have some specific data that we'll take a look as to what it would look like if we're measuring a proportion. Okay, you'll see throughout the rest of the semester that we're really particular that we split up. Are we talking about proportions or means? They're different measurements and they have different formulas, amongst other things. The mean of our sampling distribution, unless we have bias, should be at 0.75. This is a case, and again, that's going to be pretty common throughout the rest of the chapter, that we're going to assume we know what the parameter is. We won't get serious about that until a little bit later on. Okay? But our sampling distribution should be centered at 0.75. Again, bias is the only thing that would keep us from that, and we're going to assume that we don't have any. There is our standard deviation formula for proportions. Okay, you just have to know n and p, and that'll be pretty common. P is the proportion that you're measuring. In this case, we know it's 0.75. N is your sample size, which again we're told is 1,000. You can, by the way, a lot of times when you see this, you might think n and p. That makes me think of binomials, where we had to be really particular that we stated n and p. Kind of the same. Proportions, if you really get down and apply bins, proportions are basically binomials. Okay, we don't use the binomial app on the calculator because you'll see in the next step, if we have enough data, binomials turn normal, and now we're in a position where we have a big enough sample size where we just use the normal approximation. Should have 0.75. 1 minus p is 0.25. Let's put the answer down here. You would get 0.0137. Okay? So if you want to think about this as percents, we're expecting to get samples that are somewhat close to 75% of our online video watchers. I think the question was also daily. Do it daily. Though it doesn't say that in the problem. But on average, we would expect our samples to vary by 1.37% from the mean, which again was 75. Which isn't that much, because 1,000 is a pretty good sample size. Anytime that standard deviation comes up, make sure to check the 10% condition. Okay? The formula for standard deviation we have there works for samples. Okay? It's not the standard deviation of the population, and as n gets really close to the population size, this formula is not going to work. So we have to stay within 10% to make sure that we're truly sampling and not approaching taking a census. I took a sample of 1,000, so I times that by 10. As long as my population is at least 10,000, okay, I'm certain, given the context of the problem, it's probably much bigger than that. I think we're good on the 10% condition. All right, for normal, n times p, we can steal some of that binomial language and say that's the number of successes. N times 1 minus p were failures. So those that fit what we're measuring and those who didn't, those have to be at least 10. And this actually came up in Chapter 6 a little bit, where we just briefly touched on the fact that, hey, if you have at least 10 successes and failures, binomials start to turn normal. Same deal. You'll see, though, if we take a good sample size, it doesn't tend to be all that close. Okay, we have 750 successes. Twenty-five 25% said no. So the two numbers I have to verify that are at least 10 are 750 and 250, and they are. Okay, so if I wanted to do any approximations about anything probability based, normal CDF is in play and I could use it. Last but not least, down at the bottom, what if we got real serious and we took our sample size up to 9,000? We said repeatedly in section 1 that n goes up, sigma goes down. And 9,000 is a really, really large sample size. Your standard deviation would be like 0.4%, like less than 0.5%, which would basically just tell you that if you took a random sample of 9,000 18 to 29-year-olds, you would get an approximation for P that is probably quite accurate to what the parameter actually is. And again, notice it went down from up here. We took the sample from 1,000 to 9,000, so our standard deviation of our sampling distribution, as expected, went down. All right, we're inching closer to the 4-step. I'm still not going to expect you to use it in Chapter 7. I will here, particularly for the plan step. You've got the context here. Again, we're assuming we know the parameter that 80% of the middle schoolers are planning to attend a 4-year college. Okay. Again, I know that seems kind of weird, like, hey, why are we dealing with sampling distributions if we just know the parameter? That, after we're kind of done introducing sampling distributions, that won't be the case anymore. We're just not quite ready for that yet, to see what it looks like without knowing what it is. What are the odds we could take a sample of 125 and that puts us within 7% of our parameter? Okay. So the state typically lays out what we're going to do. Plan, this is what I wanted to show you, even though you're not going to be required to set up your answers as a 4-step yet. Chapter 8 we will. If we do a 4-step, the plan is typically where we address conditions. Okay. Basically, it's about checking on bias and making sure we're good to use a normal approximation. Okay, that's really what it's all about. So condition number 1 is called the random condition, where we should look through the problem and make sure that it tells us that our sample of 125 was taken randomly, and it does. So I just need to write one sentence that we took an SRS of n equals 125. Now in the do step, when I calculate the odds that we would get a sample that puts us within 7%, that's where they're getting the 73 to 87. That's 7 below to 7 above, 80. I'm going to use a normal approximation, so I just got to make sure that I can. N is 125. P is 0.8. That's 100, which is obviously at least 10. 125 times 0.2, that's at least 10. So under the do step, when I go to make this calculation, we can use the normal CDF. Okay, successes are students that are saying they're planning to attend a 4-year school. We have 100. and our failures are those who are saying they're not. As always, keep in mind, use those terms loosely. It doesn't make any implication about good or bad, right? Success is just what we're measuring, and that is students that are attending a four-year school. We've got 10 of each. So we can use the normal CDF. All right, so down in our do, we've done these before. This would be where we're going to go draw a normal curve. This normal curve is going to be centered at 0.8. Our standard deviation would be 0.8 times 0.2 so about 3.6% of variation on average from the mean. Okay, a little bit more than the previous slide. Our sample size is a little smaller. And then we are looking for these outcomes here to here. We'll shade the probability that we're going to calculate. You've got mu and sigma, lower bound of 0.873, upper bound of 0.87. You could go normal CDF that, and you, certainly if you have a calculator, feel free to try. You should get 0.948. So in the conclusion, we'll summarize what we found, that 95% of SRSs of n equals 125 would give you a sample proportion within 7% of the parameter. So at that sample size, there's a really, really good shot. It'll put you within 7% of P, our population proportion, which we knew was 0.8.